So yesterday we started with the sixth lesson, that is multiprocessor architecture. In that we had seen the first topic, that what do you mean by multiprocessor. So a multiprocessor is nothing but a system which has a different or a multiple cores of a processor, but an operating system or the computer system remains only one. But if we compare multiprocessor with a multi-computer, then in multi-computer we have more than one computers, and on each of the computer we have different operating system and we have different processors. So more than one computer becomes multi-computer, and more than one core of the processor is considered to be as multiprocessor. So we had seen that a Flint's has developed a different classification of the computers. So there were four classification. First was SISD, which was nothing but single instruction, single data stream. Second was SIMD, single instruction, multiple data stream. Third was MISD, multiple instruction, single data stream. And last was MIMD, which was multiple instruction, multiple data stream. So what was happening in first single instruction, single data stream? My instructions were given from the control unit to the processing unit. Processing unit was completing the execution of the instruction and passing that data to either get stored in the memory unit or to get it displayed to the user. So we were using only we were executing only one instruction, and the data was passed to the memory for storage and to the user as the output by using only one data stream. So since there was no parallelism, and to achieve that parallelism, we started using SIMD. Now what is that SIMD? It is nothing but single instruction, multiple data stream. What was happening in that? Again, there was a single instruction getting executed, but we had multiple data stream. So how this single instruction was executed on multiple data stream? So to achieve that parallelism, we were dividing the main instructions into sub-instruction, and those sub-instructions were executed on different data streams. So we could achieve little parallelism, which was not there in SISD, as well as the execution of instructions were happening little faster as compared to that of SISD. Then next we had seen what was MISD, multiple instruction, single data. What was happening in multiple instruction, single data? We had a single data stream and the multiple instructions were coming. So the procedure up till execution was faster, but the procedure for storing the data into the memory and displaying it to the output was slow. So to overcome that, we started using MIMD. Now what was happening in MIMD? Any multiple instructions can be executed and they can be transferred and stored to the memory by using multiple data stream. But the memory was shared among all these different processing units so that they can accumulate or they can store the data into one main memory and not into different locations of the memory. Okay. Then we had seen what was instruction pipelining. That means if I want to execute more than one instructions or to achieve the parallelism, we were using the concept of pipelining. Now, how was that pipelining done? We were dividing the programs into different tasks, or one program was divided into sub programs, and those sub programs or sub tasks of the main program was getting executed at different timing units. So to achieve this, we had seen that our instruction was having, or the program was divided into instruction, and how that instruction was executed. First we used to fetch the instruction, we used to decode the instruction, then the address was being generated for the particular operand. Then the operand was fetched from that particular address. Instruction was executed. We used to write the result and we used to update the program counter. So all these 7 steps were indicated with some, were divided into 4 stages. Those 4 stages were FI, where we used to do instruction fetch. Then second stage was BA, where your decoding was done and address calculation was done. Then was FO, the third stage, where your operand was fetched. And the last was EX, where your instruction were executed and result was returned. So when I'm executing the first instruction and when I'm fetching the first instruction, in the second step, I will decode that instruction. In the third step, I will fetch the operand. And in the fourth step, I will execute. But when the instruction 1 is getting decoded, I can fetch the instruction 2. Similarly, when first instruction is getting or fetching the operand, I can decode the second instruction. When the first instruction is executed, I can fetch the operand of the second instruction. and then I will complete the execution of the second instruction. So I can simultaneously start the execution of the instructions depending upon all these 4 stages. So if one is fetched, the other can be decoded. If other is getting decoded, the third can be fetched. If the first previous instruction is fetching the opcode, I can decode the next instruction, and if the previous one is getting executed, I can fetch the operand of the next instruction. So by using these 4 stages of pipelining, or by dividing the instruction into these 4 stages, I can achieve the pipeline. Then next we had started with a topic called as bus arbitration. Now what was bus arbitration? To execute or to transfer any data from one device to another device, we were using a concept of bus arbitration, where every device which wants to transfer will be considered as a bus master. And if a device that wants to transfer will have to first request for the bus. If that bus is busy, the device will be made wait. If the bus is free, the device will be allocated with the bus as soon as by the bus controller, and the device can transfer the data. So we have seen that there are 3 methods for bus arbitration. The first was daisy chaining, second is polling, and the third is independent request. Now out of that, we had completed with the first one, which was daisy chaining. So what was happening in daisy chaining? We had a bus controller which was controlling all the 4 buses, that is the bus grant line, bus request line, bus busy line, and the data transfer line. We had different units, or we can say different system connected to all of these lines. So whichever device wants to transmit or wants to transfer the data to any other device, and if it gets that bus, that device will be considered as a master device. So if a device wants to transfer, I will first request for the bus. So my bus request will go from the bus request line. If that bus is busy, the bus busy line will be activated to that particular system or to that particular master device, which will be assumed that the bus is right now busy, and if I have to check again if the bus is free or not. If that bus is free, the controller will generate a bus grant line to the master device. When the bus grant is generated to the master device, the master is supposed to assume that the bus is allocated, and then the data transfer can be done. So what was the advantage of this system? That it was very simple. Whichever device wants to transfer, just send a request, check if it is busy. If it is busy, wait for some time and again send a request. If it is not busy, that means if it is free, immediately the bus will be allocated and the data transfer can be done. We had very less number of control lines. How many lines? Only 4 lines. One was for request, one was for busy, one was for data transfer, and other was for bus grant. So we had very limited control lines. So every device was connected to all of these 4 lines. So even if I increase the devices, I can easily increase the devices without increasing the control lines. Why? Because all of these devices, whichever I am connecting, every device is going to share a same line. But what was the disadvantage? That if any other device wants to transmit a data, and if the bus is busy, that device has to continuously keep on waiting, which is called as starvation. So the disadvantage of the starvation was there in the daisy chaining. So continuously the device has to keep on checking. If it is continuously free, if it is continuously busy, that particular system which wants to transfer the data has to keep waiting. So that was all about daisy chaining. Now today we will be seeing the second bus arbitration technique, which is called as polling technique. Now if you see in the diagram, again we have a bus controller. Again, we have a bus request line, we have a bus busy line, we have a data transfer line, and there are master devices, that is nothing but the system which wants to transmit the data. So whichever device gets the bus, that device will be called as master. So if system 1 gets the bus, it will be called as master 1. If system 2 gets the bus, it will be called as master 2. And if system 3 gets the bus, it will be called as master 3. But now in this polling technique, we have few more lines, which is nothing but written as poll count lines. Now what is the function of bus request line? Whichever device wants to transmit the data will have to first send a request. Where will that request go? It will go to the bus request line. Through the bus request line, it will reach to the bus controller. Now if that bus is busy, what will bus controller do? It will activate the bus busy line. So when this bus busy line is activated, what will that device understand? That the bus is busy right now and I have to re-request again after some time. What is the function of the data transfer line? If I if that particular device gets the bus, so it can transfer the data or put the data on this data transfer line and send it to any of the other device, whichever the device wants. So the function of bus request, bus busy, and the data transfer remains same as that of daisy chaining. Now, what is the difference in polling? We have some lines called as poll count lines. If you see, each and every device is connected to those poll count lines. Okay, now what is this technique doing, or why it is called as polling? Because it is the process of calling each and every master device chance by chance or turn by turn. So if master 1 has polled, the request will be given to master 1. After that, whose turn is there next? Master 2. So the turn will be given to master 2. After that, the turn is of master 3. So the request will be given to master 3. Next is master 4. So the turn will be given to master 4. So why it is called as polling? Because the process of it is what is it polling doing? It is calling each and every master device turn by turn. Therefore, it is called as polling. Now, what is happening over here is, as I said, that master is connected to each and every poll line. So if I have 3 poll lines, if you see, all the master devices are connected to those poll lines. Now, why are they connected? Because every master device, whichever is being selected, will be called by a particular address. Now, what was happening in daisy chaining? जिसको request आया, उसको reply मिलेगा. But here also, once I give the request, how will that request be served by the bus controller? Not by using bus grant, which was there in daisy chaining. Now that bus grant is replaced by these poll lines. So what is happening? Each and every master device will be having a particular address. That address will be generated by whom? It will be generated by these poll count lines. So master 1 will have some address which is generated by these poll line. Master 2 also will have some address which will be generated by this poll line. Similarly, if I have 3 more master devices, every master device will have a unique address, and that unique address is generated by these poll count lines. So what is the function of this poll count line? To generate a unique address for each and every device which is connected to itself. Now what is happening? When a bus master 1 request for the bus, where will that request go? It will go to the bus request line. Through that bus request line, it will reach to whom? It will reach to this bus controller. So now if the bus is free, so your bus busy will be inactivated, and your grant request should go to the master 1, because why? The bus is busy. Now, as I said, there is no bus grant line over here. So what is happening? The bus controller will also generate one address. Now that address which is generated by the bus controller will be matched with the address generated by the poll count line. So if that address matches, master device 1 will be allocated with the bus. So for example, if master 1 has requested for the bus through the bus request line, and the poll count line has generated an address called as 0, 0, 0, 0. When this request reaches to the bus controller will also calculate the address, and if the address calculated by bus controller is also 0, 0, 0, 0, since this address generated by bus controller, which is 0, 0, 0, 0, matches with the poll count line address for the master device 1, which was 0, 0, 0, 0. Since both of the address have been matched, therefore the bus will be given to the master 1, and then master 1 can use the data transfer line to transmit the data. Similarly, now if master 2 wants to transmit a data, so what will master 2 do? Send a request on a bus request line. Poll count line will generate an address as 0001. Since the request has reached to the bus controller will also generate an address. Now, if suppose the address generated by bus controller is 0002, is it matching with 0001? No, it is not matching with 0001. So in this case, master 2 will not be allocated with the data transfer line for transmitting the messages. So what will master 2 do at that time? The master 2 or the system 2 has to re-request again. After the re-request is done, again the poll count will generate a new address. Again your bus controller will generate a new address. And if that address matches, then only the system will be allocated with the bus data transfer line. Is this understood?
Ma'am, but why is every master connected to every poll count line?
So that it generates the address. Now if suppose if it is connected only to the first line, it might happen that my bus controller puts the address on the second line. So if it puts the address on the second line, and since my master is divided only to the first line, I will never come to know whether the bus controller has generated the address or not. What I will assume as a master device, that I have generated the address, but I am not getting the request, or I'm not getting the bus. Why? Because I'm not connected to that bus control line. So what is happening, when I connect it to all the lines, from whichever bus control line I get the address generated, I will accept it from that particular line. Therefore, it is connected to all the pole count lines, to as well as to all the bus controller line, because pole lines can generate address on any of these lines, as well as the bus controller can put address on any of these lines. Okay. Understood?
Yes, ma'am.
Is this polling technique clear to everyone?
Yes, ma'am.
Okay. So what is the advantage? This method does not favor any particular device and processor. It does not favor any particular device or processor means what? Since I'm using the concept of address, so whichever device address matches with this bus controller address, that devices will be served. So I am not keeping the restriction only up till master 1. If the address matches to master 2, master 2 will be allocated for doing the transfer. If the address matches with master number 33, master 33 will be used for transferring the data. So it is not restricted to any particular, or it is not favoring any particular device. Whichever device address matches, that particular device will be given a chance to perform the data transfer. Again, this method is very simple because we are just matching the addresses and giving the chance to that particular device for performing the data transfer. What is the next advantage? Even if one device fails, it is not going to affect any of the other devices. So if suppose during the data transfer, or not during the data transfer, in general, if master 2 fails, I can continue my data transfer with respect to master 1, as well as I can continue my data transfer with respect to master 3, 4, and so on. So the failure into one device is not going to affect any of the other devices. Why? Because each unit is individually connected separately to each of the pole line, each of the bus request line, and each of the bus busy and the data transfer line. Okay. But what is the disadvantage? If I want to add any more devices, for those many devices, my count line will always keep on increasing. So when I try to increase my systems on this particular scenario, or if I try to increase the devices, what is going to happen? I am increasing my number of lines, which is in short increasing the entire control lines or the circuit lines for the entire system. So if I say suppose have 10 master devices, for one master device, if I require 3 pole lines, so I have to do those many, or I have to increase those many pole count lines with respect to the number of master devices that I am adding inside the system. So this does not mean that you cannot add the devices. You can always add the devices, but it is going to increase those many number of pole count lines.
Ma'am, but what if it only one pole count line is given?
Now see, it might, if there's only one pole line, so it might happen that the address which is generated by this particular pole count never matches to this. Whatever goes for bus controller with bus controller line, same goes for the master with the pole count line. Because, and why I am connecting this to everything, because this master device does not know that whether first line will be generating the address, or second will be generating, or third will be generating. So I have to keep on increasing the count lines depending on how many master devices I am using, and I have to connect all those lines to all the pole count lines which are there inside the system. Because what is that polling doing? It is giving the chance to the master devices chance by chance. At a time, it is not serving 2 devices, it is serving only 1 device. So it might happen that continuously master 1 is only getting chance and master 2 is never getting chance. Why? Because I have not connected to all the lines. So if I do not connect this to all the pole count lines, or if I do not have n number of pole count lines, it might happen that there is only one device which is continuously getting served, whereas the other devices are always sitting idle and they are never getting served. So for this reason, we have to increase the count lines, and for every count lines, we have to connect each and every master device, and we have to see that they are also connected to the bus controller line. Okay.
Okay, ma'am.
Now all the disadvantage which were there in your polling and daisy chaining concept are eliminated in your independent request. Now as the name says, independent request means what? Every device has separate bus request and has a separate bus grant. So in this case, there will be none of the devices which will be waiting. Why there is no device which is waiting? Because every device has a separate grant, every device has a separate request. And if you see in the diagram, we have a bus controller which is common, we have different devices, and we have a data transfer line which is in common. But if you see, the bus request and the bus grant is separated for each and every device. For master 1, the grant is grant 1 and request is request 1. For master 2, your grant is grant 2, your request is request 2. For master n, grant is grant n and request is request n. So with this, what is going to happen? I can have both of the devices, that is both of the master device communicating at the same time. Why they can communicate at the same time? Because they can request through the separate request line, and they will grant the bus also through the separate grant line, and they can transfer the data through its own data transfer line. So when one is working at the same time, your master 2 can request for the bus will be granted to it, and the data transfer can be done. Similarly, at the same time, master device N can send a request, will get a bus and can do the data transfer. So by doing this independent request, every device is sending its own independent request, and it is getting the grant as soon as the request is received. I do not have to check whether any of the device is waiting or not. I do not have to check whether the address is generated or not. I do not have to check whether the address is matching or not. As soon as I request, immediately in the next minute, I'm getting the bus and I'm doing the data transfer. So since the response is faster, therefore the execution or the data transfer is much more faster as compared to your polling technique and your daisy chaining technique. But if you see the diagram, or if you compare the diagram, the number of hardware lines are increasing as compared to polling and daisy chaining. So since every device has a separate request and separate grant, so if I add more number of devices, for each and every device I have to connect two lines extra. Which two lines extra? One for the request and one for the grant. Okay, so the number of devices I attach, the number of hardware will be increased, and that will be even more as compared to the polling system. Okay, in polling system, what I'm doing, even if I'm connecting the hardware or if I'm connecting the device, I am increasing the count line, but I'm keeping the request and the busy line as common. Whereas here, for every device, I am increasing the bus grant also, as well as I'm increasing the request line also. Okay, but if I compare with the execution or with the data transfer rate, independent request is achieving more faster response as compared to your daisy chaining and as compared to your polling, because the waiting concept which is there in daisy chaining and polling is eliminated in independent request. Is this clear?
Ma'am, but if I have more masters than the number of buses, how will
Yes.
everyone get the bus at the same time?
Sorry, can you repeat? If you have more master,
Then the number of buses.
that is not possible only, no? Because what is there in independent, if you are attaching a master, you have to give us bus grant and bus request. अगर आपने वो मास्टर अटैच कर दिया और रिक्वेस्ट और ग्रांट लाइन ही नहीं दिया, that means you that device cannot be used for data transfer only. Why it cannot be used? Because I cannot share these lines with that new device, because these lines are dedicated only with this master. I cannot share these lines with any of the other master. Therefore it is independent request. So if you increase the device, you have to put the lines. If you don't put the lines, that device is of no use. That means it cannot be used for data transfer. Understood?
Yes, ma'am.
Okay. So is this clear? All the three bus arbitration techniques?
Yes, ma'am.
Girls?
Yes, ma'am.
Okay. So with this, we have completed the syllabus of computer organization. Sixth chapter had 3 topics: Flynn's classification, instruction pipelining, and bus arbitration.